Good evening, everybody. This is Mark Miller, Executive Director to the Passive House Alliance United States. I'd like to welcome you to tonight's presentation. Topic will be selecting the ideal ductless heat pump for passive house designs with our very special guest, Mr. Mark Kuntz, who is the Manager of Strategic Accounts at Mitsubishi Electric, and he's located here in Chicago. Presentation is taking place tonight at the Heifele showroom in downtown Chicago. I'd like to thank Mark for providing us the presentation tonight, and especially to thank his company, Mitsubishi Electric, for being a sponsor to the Passive House Alliance US. We appreciate their support and happy that we are partnering with Mitsubishi as we grow the Passive House movement here in the United States. I'd also like to thank some of our other sponsors, Heifele Corporation, makers of fine architectural hardware. We'd like to thank them for hosting the Passive House Alliance Chicago chapter for all of our meetings throughout the past year. Certainty, Saint-Gobain, and Isover. Intus Windows, makers of fine European windows. Prosoco Corporation. Ultimate Air, makers of ERVs and HRVs. Chemlink, makers of fine sealant products and roofing membranes. Zola Windows, makers of fine European windows. And Lumen Catch. And now on with the presentation. I'd like to thank Mark Kuntz for presenting to us tonight. It was an excellent presentation, and the presentation will continue to be available online at the Passive House Alliance US website in the members only area. If you need to reach Mark, if you have further questions, he is more than happy to entertain them. You can reach him at his phone or email listed here below. And thanks for joining us tonight.
It's great to be with you today. I appreciate the opportunity to talk about a great solution for passive house heating and air conditioning. I've had the opportunity to take a look at several passive house designs, and in fact, we're going to be talking about a couple of those. But what stands out, and what I know you're all very aware of, is the fact that in these super insulated homes, we end up with heating and cooling loads that are a small fraction of those of a conventional house. In fact, so small that they are a small multiple or a small fraction of what the conventional heating and air conditioning equipment capacities go down to. And if you're talking about heating and cooling capacities in the 6,000 to 10,000 BTU range, you're really talking about a very oversized system if you were to try to treat that with conventional equipment, which typically is not much smaller than 2 tons. Occasionally you'll find a 1.5 ton unit, but certainly not less than 1 ton unit. Fortunately, the ductless heat pump, also known as mini split, serves as a real ideal solution for that. And having had some success in passive house designs, we wanted to provide you some of the insights and background on how these systems can be a solution for heating and air conditioning needs in passive houses. The learning objectives for the session are to gain an understanding not only of the basics of ductless heat pumps, but to understand some of the new functionality that's been added recently. You're probably familiar with the traditional mini split, as they're also known, but a lot of things have been added, including the ability to tie multiple indoor units to a single outdoor unit, and for a heat pump to operate in extremely cold climates. We're also going to take a look at some of the new indoor unit configurations that are available, far beyond the traditional wall mount unit. There are floor mount, ceiling, and even ducted units available in the mini split family. We're going to recognize benefits of ductless heat pumps that go well beyond just their energy efficiency, especially especially in a super tight home, the ability to have actively managed airflow and easily accessed filtration components add some significant indoor comfort and indoor air quality benefits. We're going to talk about selecting optimal systems depending on where your project is. That may be based on the heating load, maybe based on the cooling load, maybe based on the latent load, the amount of dehumidification that you need to do. But in all cases, the mini split offers the opportunity to select a system that's perfectly matched to your needs. And then finally, as you put together your passive house calculations, it's a challenge sometimes to find the data that quantifies how much the mini split system is actually consuming in terms of energy. We're going to review the available resources that provide specifics on that data for both the heating and cooling modes, not just at nominal conditions, but at your actual project's conditions. And then wrap it up with a couple of some questions and answers. Just to give you a background, the mini split that you see pictured here is the traditional outdoor unit about the size of a small suitcase, indoor unit hanging on a wall inside, and the two connected basically by a set of refrigerant pipes. These typically are in the order of a 3-inch diameter bundle, which includes both refrigerant lines, the controls that communicate between the two units, and a condensate drain. All of those are bundled together and can come through a 3-inch penetration in your envelope. And as the name would imply, there's no ductwork, so there's no duct losses. These systems are extremely efficient with energy efficiency ratings as high as 26 SEER, 10.6 HSPF, and in the conventional layout as we see in this picture, they provide individual room control. That room where the indoor unit is situated has its own set point and operates independently of every other room in the house. The units are typically extremely quiet, both the indoor unit and outdoor unit. The indoor unit is typically imperceptible, even when operating at its highest speed. There's literally no noise sound, no air sound, and it's applicable for installations in master bedrooms, places where you need extremely quiet conditions to be maintained. The outdoor unit as well is extremely quiet. It's on the 38 dB range of that scale, but similarly can be placed virtually anywhere due to the fact that when it's operating, while there is a slight amount of air movement that you can detect, it's extremely quiet. We also are going to be talking in further detail, but the systems are cold climate capable, a capability you don't often think about when you're talking about heat pumps. Systems that we'll be covering in some detail are capable of producing their rated heating capacities at 5 degrees Fahrenheit outdoors, and all the way down to negative 13 degrees Fahrenheit are still producing 82% of their rated capacity. Again, a great fit in a passive house design where you've eliminated almost all of the heat loss. The little bit that remains can now be treated very effectively with a super efficient heat pump. So that's the basic ductless heat pump or mini split. The heart of the system is the inverter. And while not wanting to get super technical here, it is the black box inside that makes so many of the features available to us. And I wanted to spend a little bit of time on this. A traditional heating and air conditioning system has basically 2 speeds, on or off. And when it's on, it's operating at 100% of its nominal capacity. Occasionally, you'll run into a very efficient conventional system that's got 2 speeds, but typically that's as good as you're going to do. And if you can make the analogy to your car, if all you had was full throttle and 0 throttle, your ride would be pretty bumpy and your efficiency would be pretty low. Additionally, you'd have very great stresses on your mechanical components, which would be life limiting. The inverter in a ductless heat pump solves all of those problems. It's a sophisticated electronic control which actually causes the compressor, or in effect the engine of the mini split system, to operate just as the gas pedal on your car does. It ramps the system up and down to the exact amount of heating or cooling that's required, and it operates continuously in terms of constantly cycling on and off. This gives you a whole bunch of features that are going to help us as we heat and cool our passive house. For one, oversizing is not an issue. In a traditional system, if you oversize it, that means even worse short cycling, even more stress on the system, and uncomfortable conditions inside as the temperature continues to overshoot and undershoot the set point. With an inverter-based device, it simply throttles down to the exact capacity that's needed and continues to operate on an ongoing basis, meeting only the existing need. And so you're not ramping up and down, you're exactly targeting the set point and you're achieving it within half a degree. The comfort levels are reached quickly because in a high temperature condition where your space has warmed up and you need to get it down to conditions very quickly, the inverter actually can produce more than the nominal capacity of the system. So if, for example, you had a 1-ton system installed in a room, a sunroom that's been off or unoccupied and maybe 85 degrees, the inverter, when it has a call for cooling, detects this condition. It'll actually ramp up to as much as 1.5 tons or 50% more than its nominal capacity and brings the temperature in the room down very quickly, and then cycles back and modulates itself to just the amount of cooling that's needed. You can think of it as hitting a big hill when you're driving with your cruise control on. The car is going to throttle up to its maximum capability till you get to the top of the hill, and then as you level off, it's going to back the throttle down. The inverter does exactly the same thing. It's got extremely low noise levels because, again, you're not hearing that relay kick in and out as the compressor turns on and off. And you've got continuous circulation of air. This does two things. It eliminates hot and cold pockets because it's continuously flowing the air throughout the space. It also improves humidity control. You've got a continuously active cold coil on the indoor unit that is able to take moisture out of the air on an ongoing basis. When the outdoor unit and the compressor have throttled down to partial capacity, the indoor fan follows and also throttles back. So you're maintaining a nice cold coil, a nice cold airflow, and you continue to take humidity out of the air, even at small or part loads. Conversely, when you're in the heating mode, it throttles up and down, but when you first start, it actually holds the indoor fan off for a period of time until that coil is nice and hot, and then the first breath of air that the occupant feels when that system comes on is above 100 degrees, feels nice and warm and toasty to them, again solving a typical complaint that people have about heat pumps that are putting out cold air or colder than body temperature air in the heating mode. These systems are designed in all cases to put out temperatures above 100 degrees. It's above body temperature. It feels warm. It feels good as the space is being conditioned. So these inverters are a core of the system. They're a part of what makes all of the systems we're going to talk about work in all their different configurations. So stepping from that simple one-to-one outdoor unit, indoor unit configuration, the first generation of improvements I want to talk about is the multi-zone ductless heat pump. These systems are capable of tying as many as 8 indoor units into a single outdoor condensing unit. So you just basically have the one electrical connection outdoors, the one set of refrigerant lines going into the house that then splits into your various zones, and each of those indoor units operates on a separate temperature set point and a separate schedule. So again, unlike a central system where the whole house is either conditioned or not, and the whole house is conditioned to a single temperature, with the multi-zone approach, some rooms can be completely off if they're not occupied. Some rooms can be at 68 degrees if there's someone that really likes a cool temperature while they sleep, for example, while maybe a mother-in-law that's in the room next door prefers it more like 76. They can have their own temperature, their own schedule, and their unit will control to that set point. In total, we make systems in the multi-zone configuration as large as 4 tons or 48,000 BTUs, so it expands a bit the overall capacity range that you'll get in a mini split system. And in addition to the traditional wall mount systems that are shown and that we looked at in the previous picture, the multi-zone brings in a collection of new style of indoor units, which are available in wall mount, ceiling mount, floor mount, and as I mentioned earlier, even a miniature ducted version that we'll be taking a look at. These could be mixed and matched in the space, so you could have a wall mount unit in one room, a ceiling mount in another, and a floor mount in yet a third. And this is just a quick view. Again, people think of the mini split as being just the wall mount unit, but these are some of the configurations that are currently available. The 4-way cassette fits up into the ceiling space. It's a very compact design. It's only 8 inches deep, so it doesn't require a lot of ceiling space in order to do that. The return is in the middle, and this is where the filtration is, again, easily accessible from the space. The supply conditioned air comes out from all 4 corners, all 4 sides of that system, and these vanes that you see are actually actively controlled. They're modulating and directing the air where it's needed, both vertically and horizontally. The second system here is a low-profile ducted system. Again, a very shallow profile, about 8 inches, can fit up into some furred space with ease. And while it's not intended to replace a conventional ducted system, these do provide a nice alternative if, for example, you're conditioning a large master bedroom and have a bath, a fixed that isn't large enough or doesn't need its own separate unit. These low-profile ducted units can drop the majority of the air into your main master space and then tap off with a duct for a closet or a duct for a bathroom and save the cost and expense of putting in an entirely separate zone for those spaces. So think of the low-profile ducted system as a means of collecting 2 or 3 rooms onto a same zone with a limited amount of ducting, but to do so in order to eliminate the need for a separate indoor unit. The floor standing unit is a recent addition. It's designed to fit in the space of an existing radiator and is smart enough to know that when it's in the heating mode, it needs to direct the airflow downward. When it's in the cooling mode, it directs the airflow upward. It does all of that automatically, and similar to the other designs, puts the air into the room where it's most needed. This combination in a multi-zone configuration is, even as we speak, being deployed in this beautiful passive house residence in Stuart, Virginia. Kaplan Thompson is the architecture firm and has been gracious in allowing me to use their photo as well as their graphical representation of the home. It's semi-submerged underground. You can kind of get a sense of the green roof here that's actually part of the surrounding countryside, and it uses one of our multi-zone units to condition all 3,200 square feet of this home. You can see the multi-zone unit attached to one of the light dormers on the through the roof. That's connected to 3 zones indoors, one of which is about a half a ton or 6,000 BTUs, the other 2 being 3/4 ton or 9,000 BTUs. That unit will furnish heating or cooling to all of the zones as needed, and this beautiful home is nearing completion. About 6 weeks from now, we should be able to see some final pictures of how this all came together, but both the architect and homeowner are very enthusiastic about how the mini split is going to serve the needs here in an extremely efficient manner with independent zones, each having their own set points and schedules. Talked earlier about the ability for these systems to operate even in cold climates, and this is just a graphic representation. There's several different sizes of what we call our hyperheat unit, which have this capability to operate at low ambient temperatures. The two depicted here are the 9,000 BTU and 12,000 BTU models. As you can see, as low as 5 degrees, the 9,000 BTU model is still producing 100% of its rated capacity, which actually tends to be a bit higher than the cooling capacity. It's a 9,000 BTU rated cooling capacity, about 11,000 BTU rated heating. And so it's continuing to produce that. As the temperature drops further and further outdoors, as low as negative 13 degrees, it's still producing heat. It's doing it at a highly efficient level, and it's doing it with all of the other features of the mini split, with active management of the indoor airflow, etc. Part of the sizing process is making sure that even at that low temperature condition, there's still adequate heat for the space. And that's part of what we're going to talk about at the end of the session, is how we determine that that is in fact the case. But in the three designs that have so far used this product, even in the worst case condition and even at the reduced amount of heat output, it's been sufficient without the need for supplemental electric heat of any kind in the construction. The proof of the pudding is underway in a series of tests in Montana, where while we've been selling these units for several years, a third party, the Northwest Energy Efficiency Alliance, wanted to get a good objective viewpoint of how they actually perform in extreme climates, and installed 5 of these systems in various locations around Montana. This particular home is in Helena, Montana. It's been completely instrumented, and it's operating now through it's operated through a complete heating season. This data is a little too detailed to get into with clarity, but there are some key information pieces that we can extract from this. This is the 1-ton system. It's rated at 23 SEER, so very high efficiency, and it has continued to operate even when the outdoor ambients are as low as negative 25, which is represented on the Fahrenheit scale here. These are the outdoor temperatures during this particular test. This happened to be the 48 coldest hours in 2011 when this was being tested. The temperatures of interest are the supply air temperature, which continues to be at or around 100 degrees. That's this green line across here. The dropouts happen to be when the system goes into a defrost mode, and the fan is actually off during that period. So while the sensor picked up that dip in the temperature, the residents did not actually feel that. The system continues to operate at 100 degrees throughout these extremely cold temperatures. And the coefficient of performance, which is the ratio of energy into the system to energy into the space, continues to be between 1.5 and 2 degrees and 2 during this entire extreme low ambient condition. So what that's telling us is even when the system is operating at a negative 25 degree temperature outdoors, it's putting out between 1.5 and 2 times the amount of heat that you would get from a conventional strip heater or resistance heater. So twice as efficient as a conventional system, even in these extremely low ambient conditions. Under normal operating conditions, these systems are 3 to 4 times as efficient as an electric resistance heater, with COPs in the 3 to 4 range. So it's a solution that's available for us even in northern climates, again, something that you wouldn't ordinarily think of a heat pump being. I mentioned some of the features beyond energy efficiency, and I want to talk a little bit about those. Also put it in the context of, again, the wall-mounted unit. And while we do offer many alternatives to the wall mount unit, there are some features that it has that are unique and that in many cases will justify its use, even though sometimes there's a bit of an aesthetic concern with that. The wall-mounted unit is our lowest cost unit. It also happens to be the unit that has the highest efficiency, because the airflow pattern coming out of that is the simplest, most efficient way of distributing air throughout the space. We've also added other features to it that make it even more attractive once people get past that aesthetic concern. And the Northwest Energy Efficiency Alliance that I mentioned is doing the cold climate test has also done some customer studies on the use of mini splits and has found that in almost all cases, within just a few weeks of having the system installed, the aesthetic objection drops away. The functional benefits of having the system there in the space with you overwhelm the aesthetic, and people end up being extremely glad that they went with the wall mount unit. The first is the IC comfort sensor, which is, again, a feature of the wall-mounted unit that actually senses what's happening in the room and through an infrared scan identifies hot or cold spots in the space. The indoor unit actually has active louvers, both horizontal and vertical, and if it detects a hot or cold spot, it's going to direct the airflow to that spot for a period of time until that condition is corrected, and then it will return to a generalized modulating conditioning of the room. If a person happens to be the only heat generating source in the room, this actually has the ability to follow them around as they change location in the room and again produce comfort for the occupant as opposed to producing comfort for the whole space, which provides some additional energy efficiency savings. It's able to see, if we call it seeing, across a wide span, 150 degrees, so it can almost see the entire room. There may be a couple corners along the wall that it's mounted on that it can't quite see, but with proper placement, this arrangement can give active heating and cooling and active airflow control to almost any space that you can conceive of. The EconoCool option even takes that same functionality and specifically addresses cooling the occupant. It will focus all of the airflow on the occupant and not bother with the rest of the room. Again, a means of improving energy efficiency as much as 20% above and beyond the traditional ductless super high efficiency capabilities. It's, again, very quiet, very gentle airflow, and has throw as much as 25 feet. So a person seated 25 feet away from this system can still be targeted and have the airflow directed to them and keep almost an envelope of comfort around them without worrying about what the rest of the space is doing. Of course, if multiple people were in the room, that mode would be disabled and the system would go back to a continuous cooling or heating of the entire space. Indoor air quality is an especially important feature in a passive home where the ventilation air is controlled and the system is very tight. If we have allergens or pathogens that have entered the space, these systems have specifically three different types of filtration that are going to be constantly removing those elements from the airflow. And again, with the inverter design, whenever the space is occupied, the system is on. And so there's a gentle circulation of air at all times. And these three different filtration elements are pulling out contaminants from the air on a continuous basis. Those range from odor-causing gases to pollens and allergens, mites, dust particles, and even down to microscopic pores and viruses, which the catalyst filter has the ability to break apart and render harmless. The other benefit is that these filtration systems are there located in the space. They're inside that indoor unit. Simple hinge open, the filters can be removed. Two of those are cleanable with either light vacuuming or rinsing. The third is replaced every year. In all cases, they're easily accessible to keep the maintenance current, and the replacements are easily available through our distribution network throughout the country. Moving on, I wanted to talk a little bit about the selection process and the fact that getting the right unit for your design is easy to do once you understand how the ratings are set up. This is a typical specification sheet. This happens to be our 1.5 ton or 18,000 BTU hyperheat system. So this is the low ambient capable heat pump system that we've been talking about. You can see that it has a range of 8,200 to 25,000 BTUs. This is taking advantage of that inverter where we can dial it back all the way down to less than half of its capacity, or dial it up to in excess of its nominal capacity for that quick cooling or quick heating burst that you might need if a space has been unoccupied and has now been activated. You can see the 20.2 SEER, so extremely high efficiency. Total rated input of 1,270 watts. That happens to occur at its nominal rated output. Those give you the cooling data that you need. So if your passive heat calculation or passive cooling calculation tells you that you've got a need for 16,000 BTUs total, you can see that that's well within the range of this unit and would be a good fit. Heating similarly, and as I mentioned earlier, the heating capacity on these systems tends to be somewhat higher than their nominal cooling capacity. In this case, at 47 degrees, the system is able to produce 21,600 BTUs. Similarly, you've got the range through which it will operate and the total input at the rated capacity. So we drop down to 17 degrees. This is the 11,700 BTU rating that would occur if we did not have that hyperheat feature. Fortunately, when we activate the hyperheat feature, it brings it right back up to the nominal capacity. Clearly, there's an energy penalty in doing so. It requires some more electricity to produce that higher output. But again, the COP is 2.77. So for every watt of input to the system, we're getting 2.77 watts of heat into the space. So still a far more efficient way to do it than a resistance or supplemental heat strip. And then all the way down at 5 degrees, again with the hyperheat feature engaged, we're still producing that full rated capacity, and will continue to do so even as the system drops into the 0 and below, although it will taper off slightly. So this is the general overview of capacity and watt inputs. Now we want to take those to your project and its specific conditions. And that's what the charts on this page do. This happens to be on the cooling side. And what it enables us to do is take a look at the design conditions that your system is going to be operating at and put in effect a series of adjustments to that nominal wattage input to determine what the actual wattage input is, both for a worst case scenario, the hottest day of the year, maybe a best case scenario, which would be the coolest temperature that you feel like air conditioning is going to be needed at all, and then interpolate a couple of points in between. And the architects that I've worked with in establishing these wattage usages have picked 4 spots, max, min, and then 2 in between. We've calculated the wattage at each and then made a weighted average of how many hours are likely to occur at each of those conditions and come up with the cooling input to the system. Similarly, those same features and data are available on the heating side, and again, pick the worst, best, and a couple interim spots, and we can come up with an overall heating wattage input. It's a little complex the first time you do it. What I've done is kind of held hands and worked with people as they go through it the first time, and beyond that, it tends to get pretty intuitive and it's easy to do on subsequent times. So I would like to extend that offer here as well. In conclusion, the ductless heat pump, we believe, provides an excellent solution that enables you to match the very minimal heating and cooling loads of a passive house to a system that's able to both scale down to that size and then within the range that the house is going to operate, perfectly match the load that exists. They operate at part load with extremely high efficiency and do so without losing any dehumidification capability or with the ability to continuously keep the airflow circulating and the house comfortable. Multi-zone systems allow you to continue to have just a single outdoor unit, but separate the space indoors into discrete temperature zones and scheduling zones, and cold climate versions of the heat pump enable you to operate these even in northern climates where heat pumps would not ordinarily be an option. An installation and service infrastructure is in place. Mitsubishi has been marketing mini splits in North America for the last 30 years and has trained over 20,000 contractors. The projects I've worked on, after the design is in place, we've been able to recommend 3 local installers who have good experience with the product to get a good competitive bid on it, and have turned out to be an effective way virtually anywhere in the U.S. to get an installed expertise in place on your project early and then bring it through to fruition and ongoing maintenance and care. And then lastly, extensive literature, case studies, and supporting material is all available on our website. The pro version of it is targeted at architects and engineers and has a bit more technical information as far as the different capacities, calculations, and case studies that we've done on these systems. I would also welcome any questions that people have as follow-up. My contact information was on the first slide in the pack. And we've also gotten a couple of questions texted in during the course of the discussion. I'll just cover these and then we'll wrap up. Question 1 is, I just installed a Mitsubishi mini split in a glassed-in porch with skylights. Since the room goes through temperature extremes, we find that it may be in heat mode for a while in the morning and then switches to cooling as the sun comes in. I believe the client has now switched off the heat. Is that the best or only option? There are a couple of options here. The system, as it's generally shipped, has a controller on it that will function in exactly the way that this questioner explains. It has a set point and then will engage either the cooling or the heating side of the system to maintain that set point. And so in a room like a solarium, it's going to have that full range, and it will switch modes during the day to treat that condition. What we really recommend is if the space is not occupied, the system should be off, because there's, again, the energy efficiency benefit of the system is that it operates completely independent of the central system, and the inverter with the excessive capacity beyond nominal allows you to take a space that's considerably out of set point and bring it back into condition quickly. So the first answer to this would be turn the system off, and then when you're occupying that space, let it decide what mode it needs to be in and get you to the conditions that you need quickly. However, there's a second option, and that is we have recently integrated our system with a conventional Honeywell thermostat that has an auto as well as a heat and cool mode. And if somebody wanted to operate it as a more traditional system for that sunroom, they could simply put it in the cooling mode. That would only allow it to come into the air conditioning mode, or vice versa, put it in heating mode and only allow it to heat. And then you'd avoid that situation of actually going through both modes in the same space in the same day. This is the Honeywell Red Link system, and again, it's a little bit more conventional feeling for North American homeowners. Second question was, do low-profile ducted units meet the same efficiency as the mini-split units? And I suspect what this questioner means is, do they meet the same efficiency as the wall-mounted units, which is the more traditional mini-split indoor unit? They don't quite match up because the ducted unit actually does require a bit more energy to overcome the resistance of the ductwork. And while we still have Energy Star rated systems in the ducted type, in a case-by-case basis, a 1-ton ducted system versus a 1-ton wall mount system, the wall mount system is always going to be slightly higher efficiency because it doesn't have that resistance to overcome. And all of that is detailed in our technical literature. You can look at the different SEER ratings on a case-by-case basis and see that there's maybe a 10% difference between those two. I believe that wraps up the questions that we had. It's been a pleasure going through these materials with you. And as I mentioned earlier, I would welcome any follow-up questions that you might have, and look forward to working with you on passive house designs all around the country. Thank you very much.
I'd like to thank Mark Kuntz for presenting to us tonight. It was an excellent presentation, and the presentation will continue to be available online at the Passive House Alliance US website, members only area. If you need to reach Mark, if you have further questions, he is more than happy to entertain them. You can reach him at his phone or email listed here below. And thanks for joining us tonight.